Margaret Gelautz. Yeah, she is an associate professor at Vienna University of Technology, Austria, and she directs a research group on image and video analysis and synthesis with a focus on 3D film, TV applications. The title of her presentation is Towards Perceptually Coherent Depth Maps in 2D to 3D Conversion. So please.
Okay. Well, thank you very much. Good morning, everybody. So, as I already mentioned, the title of this presentation is Towards Perceptually Coherent Depth Maps in 2D to 3D Conversion, and it's joint work by Nicole Brosch, Tanja Schausberger, and myself. I'm Margaret Gelautz, and we are affiliated with the Institute of Software Technology and Interactive Systems at Vienna University of Technology in Austria. So what am I going to talk about today? I'll first give a brief introduction. I'll say some words about the principles of semi-automatic 2D to 3D conversion, and then I'll focus on the algorithm we have developed. So I'll first give an overview of the whole processing chain, and then I'll focus in more detail on some of its specific components, some constraints we introduced, and one particular issue we are dealing with is to the proper treatment of objects that exhibit motion in depth. I'll then present an experimental evaluation of the algorithm we designed. I'll show the effects of different versions of the algorithm, and I'll also present a comparison to other competing algorithms. So just a few words, why do we need 2D to 3D conversion? Nowadays, there's a broad range of 3D capturing devices already available, but of course, if we are dealing with available 2D archives and we want to convert them to 3D, then those 2D to 3D conversion techniques come into the play. And there are several techniques, several ways to do that, and one of them is what we are actually using is an interactive, semi-automatic approach. So in our algorithm, we have some user-provided scribbles on the first and on the last frame, and these sparse depth values are then propagated throughout the whole video volume so that we finally get depth maps for every frame throughout the whole sequence. And some of the challenges we encounter in such algorithms is the topics of coherence. So we want to achieve spatial temporal coherence. That means that the edges in the computed depth map, depth video, should be aligned with the edges in the input video. And also we want to achieve perceptual coherence, which means in particular that our depth result should be consistent with monocular depth cues, and in particular we're taking a look at occlusions that were caused by object motion. So here is an example of what I mean by perceptual coherence. Let's take a look at this section of a video. So we have the small dragon in the background that's coming closer. There's another dragon in the foreground, actually the big one here, and there at some point in time the small dragon comes further in the foreground, so it's actually occluding the bigger object, the bigger dragon in the background. So it moves on. And what happens now in conventional 2D to 3D conversion? Let's assume we have an input, several frames of the input video, first frame, the last frame, and an intermediate frame, and the user is drawing some hopefully comfortable scribbles on the first frame. So the depth encoding is given here. So bluish colors of the scribbles, they mean the object is in front, and the yellow and the reddish colors, they denote objects that are further in the back. And in particular, if you take a look at the small dragon here, it's annotated in yellow, so it's rather far in the back, and on the last frame here, it's annotated in blue. That means that it has come, in the meantime, it has come further to the front. Thank you. All right. How do I? Where?
Press right there.
Okay. So, and what happens now if we just do a straightforward depth interpolation between the first and the last frame for this particular scribble? That's when we might come to perceptually incoherent results as shown here, because here the dragon, the depth value that's computed for the dragon on that intermediate frame, it actually indicates that the small dragon is still behind the bigger one, behind the big dragon, whereas the input video shows us that the occlusions in the input video show us that it's actually the other way around. So that's an undesired effect that might come from a very straightforward depth interpolation. And we, in our algorithm, we want to cope with that. Some of the related literature I'll just shortly mention. We start out with a video object segmentation algorithm that we extend to work as a 2D to 3D conversion algorithm. There are 3 competing algorithms listed here. Reference 1, work by Gutmann, 3 by Fan, and 4 by Ivancic. So we'll compare our results to those 3 algorithms. And the last 2 references, they refer to data sets that we are using in our tests. It's the Sintel and the new Tsukuba data set. So let's now come to the algorithm itself. This is an overview. It contains several blocks. I'll just focus on the most important ones. And probably the most important one, that's the cost volume filtering block here. So based on the initial scribbles provided by the user, then we are able to construct a cost volume that's based on color histograms from the input image, especially from those pixels that were covered by the user-provided scribbles, and we do a filtering of the cost volume, an edge-preserving filtering using the guided image filter to come up with the filtered cost volume, and then finally there's a depth assignment block which outputs the final 3D video. And here is one feature that's important to us. It's this temporal coherence block. I'll show on the next slide what we did here, as opposed to conventional stationary filtering where the filter window is placed at is centered at the same pixel in consecutive frames. We first do an optical flow computation, and then we use the motion vectors to displace the filter window according to this observed motion. So that's one feature of the algorithm. There are several other blocks which I'll just mention very shortly. STC, that's a spatial temporal closeness constraint, and CON, that's a 3D connectivity constraints. And these 2 constraints, they help us limit the influence of the user-provided scribbles onto those pixels that are located in the vicinity of the pixel, or those pixels that appear spatially connected in 3D space to the initial pixels. And here is now DC is the depth change module. That's the part that tries to take care of the perceptual inconsistencies, which I explained in the beginning. And the basic idea of this module is that we do a detection of occlusions based on motion vectors, and these occlusions then help us determine the right depth order of individual segments. That's shown in some more detail here. So we have an intermediate frame of the input video, and the colors here in this segmentation, they actually correspond to the colors, the user-provided colors, which mean depth values, in the on the first frame. And from the optical flow vectors I mentioned, we derive occlusions. They are computed by detecting inconsistencies between the forward and backward optical flow, and the motion vectors also give us information on which segment is in front of the other one. And this directed occlusion is shown by the arrows here. So for example, this arrow is pointing from the light blue to the red area, so that means that the red segment is further in the back and it's partially occluded by the light blue segment. And a similar situation arises here, where this little dragon, which was annotated in yellow at the beginning, which is partially occluding already the light blue region. We can now use this information, this partial occlusion information, to construct a graph. It's a non-cyclic directed graph. The nodes here correspond to the segments shown here. The edges encode this directed occlusion information, and furthermore, from the first frame, and in some cases also from the last frame, we have depth information. So in some cases, the depth is fixed when the object wasn't found to move in depth. In some words, in some cases, like for the yellow, the dragon here, there is a depth range that was derived from the user scribbles in the first and in the last frame. And we can now use the information in this graph here to automatically refine the depth information to derive some depth constraints for each intermediate frame. And the important thing is that these newly computed depth constraints, they are consistent with the occlusions that we observed by our motion detection. So that's the basic idea of this algorithm, of this part of the algorithm. That's what I said already. And let's now come to the evaluation part. So how did we set up our experiments? We had a range of test data. Some of them were computer-generated test data, especially the Sintel data set and the new Tsukuba data set. And those synthetic data, they came with ground truth information. From the Sintel, we had the ground truth optical flow information, and then we also had ground truth depth information. So that's important, the depth information for validating our approaches. So for the synthetic data, we had synthetic depth data, of course, and then we had also some self-recorded scenes for which we could compute stereo-derived depth, and in those cases we used the stereo-derived depth as reference. So the scribbles were then initialized with the values from the depth reference, so that's a little bit different for the evaluations. And then we carried out a quantitative assessment. We tested the effects of different modules of our algorithm, the effect of the motion-guided filtering, and also the sensitivity to optical flow results. So let me now show some of the results. First, regarding the perceptual coherence, that's the example I showed in the beginning. Here we have the input frames, here the ground truth depth values, and as I already pointed out in the beginning, there are some perceptual incoherences regarding occlusions if we just use linear depth interpolation, and with our depth order guided interpolation, we were able to correct these perceptual incoherences. Then we did quite a thorough evaluation by switching on and off different sections of the algorithm, different modules. So I won't explain all of that in detail, just give a broad overview. The orange results here, they were computed without considering the depth changes of the objects, and then the greenish results here, they did a straightforward linear interpolation, and the blue results here, the depth order guided interpolation. So in that case, the results, actually the depth order guided interpolation didn't improve the quantitative results. However, this was a test using ground truth optical flow. Optical flow is used at several steps of the algorithm, and if we now switch to estimated optical flow, which of course has some errors included, then we see that now the depth order guided interpolation also delivers quantitatively, results that are quantitatively a little bit better than the straightforward linear interpolation. And what we can also see here, we have here TC refers to temporal coherence, that's the motion-guided filtering, and in all cases, both for the estimated and the ground truth optical flow, the motion-guided filtering was able to improve the results. So this is a comparison to 3 other algorithms, and if one takes a look at these figures here in more detail, we find that our results, which come in 2 versions, the winner takes all and depth blending, depth assignment scheme, basically we outperform algorithm 1 by Gutmann in most of the cases. The same applies to the algorithm by Fan, and we deliver very similar results to algorithm 4. So in 4 or 5 of the 11 test cases, we outperform them. So that means, in summary, the results of the algorithm are competitive with other state-of-the-art algorithms. And finally, this is just a visual example of how the algorithm can improve the depth interpolation. So we have the ground truth results here. The results by Fan, they have some some artifacts here in the depth reconstruction, for example, on the shoulder here. And also the algorithm by IS&T has similar artifacts on the head of the statue here, whereas our result seems to deliver the visually best results. So that brings me now to the end of the talk. Just to summarize very quickly, I've presented a semi-automatic 2D to 3D conversion algorithm. It takes a step towards the generation of perceptually coherent depth maps. We took special care to incorporate motion-based occlusion information to generate that perceptual coherence. Then the inclusion of motion-guided filtering led to an improvement on average of about 16%, and the results were quite comparable to other state-of-the-art algorithms. So what we might take a look at in the future, what we haven't done so far is we didn't care about the efficiency of the implementation, so there's clearly room for improvement in this aspect. And also regarding the initial scribble matching strategy, which I didn't cover in detail, and now there is some room, some possibility for improvement in terms of additional user support. So that brings me to the end, and thank you very much for your attention.
Thank you.